How was your drive?
Uh, bad.
Yeah. Yeah, was
I
it like,
It was like really bad actually.
mhm,
The
mhm.
snow was bad like in Boston, but where I live it was just raining and windy. But on the way back I was like hydroplaning and it was so bad.
Yeah, and you lived in Jersey, right?
Yeah.
Got it. Well, I mean, at least you got home safe.
Yeah, I lost a hubcap in the
Oh, it's so
process,
neat.
but yeah, but
Uh,
it's better than like anything else, I guess.
yeah, how did the hubcap get taken out?
That's a good question.
Pothole or
I
something?
think, well, I guess when I was, there was only one time where it was like really bad and
Mhm.
I hydroplaned and I like,
Mhm.
I'm so happy there were no cars in the other lanes because I went like
Yep.
all the way across the highway.
Oh my,
Um,
yeah.
so I'm assuming that's how it happened.
Got it. Got it. Got it. Okay, so let's see. These calculation problems you sent me, and then equations that you sent me as well. So, um, okay, let's see. I'll open up like a whiteboard. So, um, yeah, why don't you walk me through like, oh yeah, you can get the questions as well. Okay, so for this problem, you said that it took you some time.
Yeah, when I first did the problem,
Huh?
I was trying to match up the units, but
Mhm.
I also didn't realize that coulombs was amps times seconds, so like that was an issue. The second time I did it, it went a lot better.
Mhm.
Um, I think writing out the units helped.
Yeah, totally. Um, so yeah, instead of like, so yes, this part's true over here, but it's best to think like, let's think about it like conceptually, right? So for instance, if we have some circuit thing like this, and well, what we are having happen are, electrons being moved, right?
Hmm.
And so if the current indicates so the current indicates, it's kind of like the equivalent of velocity, except instead of it being like meters per second, which is like, traveling a distance per unit time, it's the charges, number of electrons passing by per second, which could be translated into the number of coulombs or charge per second.
Hmm.
So what I would have, yeah, I want you to be thinking is, so when you're reading this, it says, assume that this battery charges for a time of 600 seconds with a current of 5 amps. Right away, you should be thinking of an amp being in coulombs per second,
Okay.
and then the rest of it would be pretty much what you ended up doing. Um, but yeah, just to be able to think conceptually, like instead of just, because instead of like kind of like just having to memorize that this is like a coulomb is equal to an amp times second, you can think of it as current is just the flow of these electrons, and therefore the number of these electrons that have charge, in coulombs per second. Think about it that way.
Oh,
Okay, now the other one, this one, you were saying that, so I see from your work, like, let's see, you wrote like, what is this thing here? Um, like,
uh, oh, I think I was writing that there was no there was a zero electric force, which meant that the charge of Q1 had to be positive because it was in the same direction as the -2. So in order to balance them out to make a zero like electric force, it would have to be positive.
okay, now what's this?
That it's like so it was the negative charge. I kind of was like making a proportion for them, like -2 per 10 centimeters would equal whatever the charges of Q1 over 20 centimeters because it's 20 centimeters away from Q2.
Huh?
And those have to be equal because the force is zero.
Got it?
But then that gave me four, which was a possible answer choice, which is why I said that I would have probably chosen four, um, without multiplying. And I'm still a little bit confused as to like why I would have to multiply if I already had the distance accounted for like in my proportion,
Mhm.
or like if that's even a good way to go about it.
Got it. Um, Here. So, um, actually, so, sorry, I was looking for my work here, but okay, whatever. I was trying to look for my work when I did this, but I think that, Okay, so for this, okay, so good job on being able to determine that the charge must be positive, so we can get rid of that. But when it comes to the proportion, though, what we would have done would be so okay, so like okay, we know that this is positive. Do we know what charge well, I guess we do because or rather okay, sorry, they're asking about Q1, okay? Now, how do we know the charge of Q2?
Um, well, I'm not sure. Because I guess it uh
So let's try some stuff out, right? So let's say that this is let's say Q2 is positive, right?
if it was positive, then there would be opposing or attractive forces between Q2 and the negative charge and Q1 and negative charge.
Yep. So like, I'm calling the middle one QM. And so if Q2 was positive, it would be experiencing a repulsion. So I'm going to call this the force of Q1 on Q2, right? And there would be an attractive force between QM and Q2. So I'm going to call this the force of QM, comma, Q2, right? Now, let's say that, so down here, I'm going to say if Q2 is negative, that in this direction would be a repulsion caused by QM on Q2, right?
Yeah.
And this way would be an attractive force between Q1 and Q2, right?
Mm-hmm.
So now since Q2 experiences a zero net electric force, it means that whatever this is would be equal and opposite to whatever this is, which also means they'll have the same absolute value, aka magnitude, right?
Yeah.
So F of Q1 on Q2 should be equal to F of QM on Q2, right?
Yeah.
Which means that it doesn't even matter what the charge of Q2 is, right?
Mm-hmm.
Because whether it's positive or negative, one would be due to the effect of QM on Q2, the other one would be due to the effect of Q1 on Q2, but they're going to be equal in magnitude. So from there, I would then bring in Coulomb's law of, I'll just do like the little k Q1 Q2 over R is equal to little k QM Q2 over R, or rather over R squared. And we can cancel out the k's. we could even cancel out the Q2s, right?
Mhm.
And now what we can do is we can solve for, because they're asking about Q1, we can solve for Q1. So Q1 would be Km times, so I'll say this R, what should I call it? I'll call it like R1 comma 2, and then this one Rm comma 2. So Q1 is equal to Qm times R comma 1 2 squared over Rm2 squared. And yep, and then you'll just do your math. So they're telling us that Qm is -2 E -9 coulombs. And always like, yeah, I would say get into the habit of just writing it out in like handling the nano or centi part when you're writing it down for the first time.
Okay.
Yep. Times, the what is this? Oh, the distance between R1 and R or between Q1 and Q2 is 20 centimeters. So I'm just going to do 20 times, uh, to the -2 or meters. And oh yeah, I would have to square that. But anyway, for the rest of the math, let's see. Yeah, I'm trying to see if, because okay, then this should be the 10 E -2 meters squared. But yeah, I mean, like, so yeah, you got the right answer. I'm just trying to see. Well, I guess you're like when you're doing this proportion here, because I mean, you could really just kind of like, double this, right? To get that. But okay, you still did a great job. You got it right. So, okay, let's look at the balloon problem. Where did I send that? Okay, so you were saying something, you said about this.
Yeah. Um, this one gave me a lot of trouble because I
Mhm.
like if I had to guess and I was timed, I would have probably went with C, but I don't understand why you're subtracting densities.
Mhm.
So I think there's a conceptual thing I'm missing.
Got it. So, what is like the buoyant force? How does that work?
It's the force of a fluid on an object or like the upward, like in this scenario, the buoyant force would be the like fluid in the balloon, like holding the load up.
So, let's say we have some, okay, let's say that we just have a table with some object on it. It's experiencing a gravitational force of mg. And sure, it's going to be a normal force of like whatever, -mg. But if we had, I mean, that's if there's a normal force, but if you didn't, and it was just a regular box, it would just be the force of gravity, right?
Yeah.
All right, now let's say that we have some water here. This is still going to be the force of gravity bringing it down. However, there's going to be a buoyant force in that opposite direction, right?
So is the buoyant force the normal force then?
Nope. So the buoyant force is equivalent to the weight of the fluid that it is displacing.
Okay.
So this is rho VG. Rho is, so let's say this is water. Rho is the density of the water. V, volume, is the density of the is the volume of the displaced water.
But if the normal force is like equal and opposite of gravitational force, like so mg, then isn't the buoyant force also mg? Like density times v times g, isn't that also mg?
So so the normal force that I drew here is because it's like sitting here on a table and not moving, so the gravitational force would equal the normal force. In this example in the middle, there's no table, so there's no normal force. And it's only the gravitational force, which means it's just gonna fall down. Um, in this beaker of water, the normal force, I mean, there isn't normal force, but you could see that there's an opposite force opposing that of gravity called the buoyant force. And yeah, it's like it's represented by, or what the buoyant force means is that in order for this object to be like submerged at this depth without it sinking if it was to sink further, we would have a stronger gravitational force than the buoyant force. And if it was a stronger buoyant force, it would be floating up more, but it's
Mhm.
just submerged here. So that's going to mean that the buoyant force and the gravitational force could be equal. But the thing is that the buoyant force is, so like the normal force is just, we pretty much just do the opposite of the gravitational force. But the buoyant force involves specifically displacing the object's own weight in the liquid or fluid that it's in. So that can be expressed as the density of the water or the fluid, the volume of the fluid that's displaced, and then G. And now
Mhm.
for the force of gravity, which is mg, the key thing that you can do here is to recognize that, well, if rho is mass over volume, right?
Yeah.
I could solve for m in terms of rho by setting it equal to rho times volume, right?
Yeah.
So I could rewrite this as rho of the object, volume of the object, times little g, right?
Hmm.
Good. So now we could, okay, so now this balloon here is filled with hydrogen gas and it's surrounded by air. So what's responsible for the weight of this balloon and what's responsible for the buoyant force of this balloon?
Um, like without the load, like just the balloon. Um, the helium that's inside would be responsible for the weight,
Yeah.
and the air is the fluid that's responsible for the buoyant force
Yep. And how can you tell?
because the balloon is like fully immersed
Yeah.
in it.
Yep. Yeah, it's displacing. So the buoyant force is always going to be the fluid that's displaced, and the balloon is displacing the air around it. Okay,
Mhm.
right? So yeah, um, basically that. And a lot of times you can also have for something that's fully submerged, you could have the volume of the object. So if it's fully submerged, the volume of the object would be equal to the volume of the fluid displaced, right?
So it's the volume of the object rather than the volume of the water or like whatever fluid it is.
So what are you asking exactly?
Like in the top equation for rho VG, that volume is also for the object, or is it for the fluid?
Oh, I see what you mean. So, it's for it. So this is going to be the volume of the fluid displaced, whereas the volume of the object here is just the volume of the object. Now, so now, okay, let's say we had a scenario where half of an object is submerged, right? That
Yeah.
would mean that the volume of the fluid displaced is half volume of the object.
Okay.
If that object, so because the object is halfway submerged, which means it can only displace half of its own volume in that fluid.
Hmm.
But if something's completely submerged, like here, then the volume of the object would be equal to the volume of the fluid displaced, right?
So we're never talking about like the volume in general of the fluid, like if it's in a beaker, like the volume of the beaker.
Correct. Correct. Yeah. For buoyancy, we're only concerned with the volume or the weight of the fluid that's displaced.
Okay.
Has to displace it. Um, yeah. So that's where you get, yeah, both of these values. So for instance, so they're giving us okay, so they're asking for the maximum possible load that can be lifted by the balloon. So we're gonna do, so okay, yeah, we're gonna have, you know, gravitational uh force here. Well, I guess I already drew it for this drawing over here. But yeah, we could just use that. So yeah, basically, we're just gonna choose one going in one direction, the other going in the other direction. Um, so we could say like, I'll just make the gravitational force be, oh yeah, so this would translate, so the rho of the object would just be the rho of the the hydrogen gas volume G, and then here it would be rho of the air. I know I wrote water, but that was for this drawing. But yeah, this one would be for air, like that. And then you just do your Newton's second law, sum of all the forces. So let's do like the gravitational or now like yeah, so I know that you wrote um let's see. Not sure why you subtract the helium because helium is lighter than air. Wouldn't it aid in the balloon in lifting? So it's all a matter, like when it comes to subtracting one over the other, it's just, it doesn't ultimately like here, I'll show you. So like I could do this is equal to like mg, which would give me rho of the hydrogen, volume of the object, g minus rho of the air, volume g is equal to mg. I can do it like that, or I could do it like, or I could do it, yeah, like this. The buoyant force minus the gravitational. So that's rho of the,
Why is the equation equal to mg again?
oh yeah, for just, so for, in Newton's second law, we have the sum of all the forces or your net force is equal to mass times acceleration. All right.
So it wouldn't be equal to 0 because the forces were like the sum of the forces should be 0 if it's not moving.
Um, yeah, so that could be something. Uh, but I think that they're saying that, or they're asking for the max possible load, a maximum possible mass of the load that could be lifted by the balloon. So we're still gonna have the balloon lift it, um, meaning that it's not going to be like it'll still be lifted upwards, you know? It won't be at a standstill.
Okay.
Mhm. So, but yeah, so over here we could just factor out the row terms for this minus this would be times V, and we can get rid of all the G's to get our maximum mass this way. And here it would just be the other way around. Um, so P air minus P hydrogen times volume is equal to M. So yeah, so both of these can work. It's ultimately arbitrary because if you choose the force of gravity value that's going down to be positive, you would just need the buoyant force in the opposite direction to be negative. But if you chose the gravitational force to be negative, then the buoyant force above going up is going to be um, positive. And I think by convention, people do up as positive, down as negative, but it's not going to play too big of a role because we see in these choices that, I mean, this one doesn't even have, this one is, I guess, just using the row of the hydrogen that's out. And this one is adding these, so that's out. And then these just have the air density minus the uh, hydrogen gas density, which means that that's, what we do over here. But it's really no different from this one. It's just going to be a difference in sign and stuff. Um, but yeah, so that's what you're doing. And yeah, since you get rid of the G terms, right, you're going to just have your answer as C.
Okay.
Mhm.
I think like I am probably still gonna have trouble with
Mhm.
fluids for a while, so maybe like if
Yep,
you have more problems
yep,
that
yep,
I can try
yep,
before the next session.
yep. Let me write it down. Buoyancy and okay. So let's see. Equations you're struggling with. Let me put that in here. Um, okay, yeah, tell me about some of these.
Well, a couple of them I was just like going through the list and I've never used them before.
Okay.
Um, so I didn't know if they were like worth memorizing, like if they come up a lot or they're kind of just like random equation.
Okay.
Um, and then the other, like the density, I wrote down like the density volume equations. Just in general, like that whole little chunk of things is kind of what we just went over, but
Hmm.
um, I'm still having like conceptual issues with them.
Totally. Okay. So density, volume, weight, specific gravity, Basille's law, expansion, kinetic energy of a photon. Um, oh, I saw like PI and what that means and what pKa actually means. Okay.
Yeah, I think I'd want to go through that as well because that was on the test today too.
Hmm.
Um, and I kind of got tripped up like differentiating between
Mhm.
PI and pKa.
Mhm. So, what can you tell me about them?
Um, well, the PI is the isoelectric point,
Okay.
and the pKa is like the negative log of Ka, which is the um like equal is it the equilibrium constant of an acid?
Yeah, could be considered to be something like that. So all of the K stuff comes from the law of mass action, which is product concentrations over um reactant concentrations. So if I had an acid HA, it would dissociate into H plus and a minus, right?
Yeah.
So I can say that the Ka is going to be like, how can I write this? What do you think?
Oh, it would be the concentration of the products over the concentration of the reactant.
Good. So, let's see.
And let's say there were coefficients in front, would those still play a part or no? Okay.
Yeah, it would turn into um exponents in this expression.
Okay. Because I'm pretty sure I don't remember which one, but like one of the K equations, you don't use the exponent, like the coefficients for, and I don't remember which one it was, but I was kind of confused as to like why you didn't use them.
Um, you should
Um,
be using them, but maybe you're thinking of like where a situation where we don't have the denominator.
um, I don't know. Maybe
Mhm.
I don't know. I thought there was one K equation that you just have the concentrations and you don't use the coefficients.
Hmm.
But maybe I'm wrong.
Mhm. Um, yeah, yeah, I guess I'll have to like look into that. But let's see. If we have, let's see how we can put this. So So okay, pKa. So okay, the stronger an acid is, the more it will dissociate. So, which means this reaction moving forward, right?
Mm-hmm.
And whenever it comes to ratios, you always want to be thinking of on what in what circumstances is the ratio larger than one, equal to one, less than one, right?
Yeah.
If we have, let's say, a strong acid, right? It will like let's say dissociate like 100%. You're gonna have an awful lot of these products relative to the initial acid concentration, right?
Yeah.
So Ka is a strength or a measure of the strength of an acid. And since pKa is the negative log of Ka, it means that pKa is going to be inversely proportional to the strength of an acid, right?
Yeah.
And so the pKa is also the pH at which there's an equal amount of um, undissociated acid and its conjugate base. Okay.
So then how is that different from the PI?
Yeah. So so overall, pKa measure of an acid strength. Now the Pi is the pH at which it exists as a Zwitter ion, meaning like yeah, Zwitter ion, meaning it's a net neutral charge,
Mm-hmm.
right? So uh yeah, so basically um you're gonna have your let's see, you're gonna have your pKa. Oh, I should also say in relation to pKa, let's say, okay, if your so when your pH is equal to your pKa, that's going to be this situation of when you have an equal amount of undissociated acid and dissociated conjugate base. Okay.
Mm-hmm.
Now, if your pH is less than your pKa, what can happen then?
Um, the the molecule would be protonated.
Yep, because you're putting it in an environment that is more acidic. Okay.
Mm-hmm.
So you're gonna have um, something like this, where the protonated form is going to be like there's going to be more of the protonated form than the deprotonated form. And then, of course, the opposite, oops, direction would be putting it in a more basic environment. And a basic environment is going to be taking protons. So you're going to have a smaller amount of that. And yeah, basically a smaller amount of this acid compared to the conjugate base, right? So so the pKa is, view that as a measure of how easily an acid dissociates, slash how easily an acid gets deprotonated. So actually I'll write this. I would say to think about it like this. At what concentration of H plus does the molecule gain or lose an H plus? Make this a bit. Oops. Yeah. Think of pKa as at what concentration does at what concentration of H plus, aka, at what pH does this molecule either gain a proton to be protonated, or lose a proton to be deprotonated. Okay. Now, isoelectric point is the pH at which the molecule can exist as the net neutral Zwitter ion. And that's most relevant for amino acids. And what you have in general is the so okay, in general, for a regular amino acid, which looks like this, our group, carboxylic acid end. So I believe the pKa here is like 9.8 or something, and I think the pKa here is like 2.2. So if you wanted to calculate the isoelectric point for a regular amino acid, you're going to take the average of the N terminal and the C terminal. So pKa N terminus plus pKa C terminal divided by 2. That'll give it to you for, a regular amino acid. When I say regular, I mean not an acidic or basic one.
Okay.
But for the acidic ones, you take the average of the two well, first of all, for acidic and basic ones, we're going to be using the side groups pKa. And so that means for the acidic ones, you're going to take the pKa of the C terminus plus the pKa of the side group of that acidic amino acid and divide that by 2. And then for the basic one, just the other way around, pKa of the N terminus plus pKa of the side group, which is also going to be divided by 2. So that's, I guess, that's how you can calculate Pi. But also on the gel itself, isoelectric focusing, you're going to have things migrate here depending on their charge as well as pH. So we can see that, whoops. We can see that for this blue positively charged. So okay, left to right is increasing pH, and low pH region is positively charged, hot because there's a lot of protons. High pH region negatively charged because there's a lot less protons and more conjugate bases and stuff. So so these different amino acids, that's what these represent, these circles, Uh,
Mhm.
so like let's say this is like glutamate or something. It's going to travel to a higher pH until it becomes neutral, a Zwitter ion. And for this negatively charged one, it's going to be moving towards that positive end until it reaches a pH at which, and the pH would be like, like let's say like 3, 4, 5, 6, 7, 8, like it's along that x-axis. So yeah, so the negatively charged amino acids and molecules will be moving towards the left until they reach a pH at which they are neutral, have no longer have a charge.
Okay.
Mhm. So yeah, so how do you feel about that? And is there any other like thing in this topic that you find to be troubling?
Well, I guess if the pKa is the concentration of like the H plus where the molecule would gain or lose another hydrogen,
Mhm.
then I mean, isn't that also the Pi? Like, couldn't that be similar because the Pi would also be like the point at which um like one like a Zwitter ion wouldn't be neutral anymore. Like if you went above or below the pi, it wouldn't be neutral.
Yep. So over here we talked about pKa being something that tells us, if something is going to be protonated or not protonated. Meaning if it's protonated, it'll have a positive charge. If it's deprotonated, it'll have a negative charge.
Mm-hmm.
Whereas for PI, these things move until they reach a region of pH at which they no longer have their charge. So for instance, a regular amino acid like this would have, let's see, this would be like a PI of like 6. So like let's say that, or here, I'll draw something like, let's say this is the thing. And we have like, okay, pH of like 2, 3, 4, 5, 6, 7, 8, 9, 10. Um, and let's say that we have a version of this that's, or let's say that we start off at a higher pH, that would give us NH2 R O O minus. So this is going
Mm-hmm.
to initially have a negative charge, and and let's say it's up here, negative. This molecule will migrate down to its isoelectric point at somewhere around 6, pH of 6. At that point, it's going to get, because it's going entering into a lower pH region, the environment becomes more acidic, therefore donates protons to this amine group to make it an NH3 positive group, right? And
Yeah.
so now we have our Zwitter ion because we have a negatively charged C terminus, a positively charged N terminus. Combined gives you a net charge of 0, right?
Mm-hmm.
So, yep. So that's how isoelectric focusing is. You essentially take some charged molecule, in most cases, that'll be an amino acid, right? And you have a pH gradient, and whatever you run that gel, you're gonna have things just move in whichever direction they need to move. That typically is gonna involve if we're going from left to right, low pH to high pH, low pH can be more positively charged because it's a more acidic environment with more protons. Um, the end with the higher pH values are a more basic environment, therefore less protons, more removal of protons, so more of a negative charge. So yeah, you're gonna have negative. So if you, so yeah, you're gonna have negatively charged things that you throw in migrate to the left until they don't migrate anymore, because at that point they stop because they become neutral, and a positively charged thing will migrate to the right and stop when it becomes neutral as well.
Okay. I guess that makes more sense.
Mm-hmm. Yep. And so, for instance, like, yeah, for the acidic ones, they're taking the average of, yeah, the smaller pKa's to get the isoelectric point. You know, and that's how it is for the different types. So, yeah, does this make a good amount more sense here?
Yeah.
Okay. Let's,
So the
yep.
PI doesn't there was like a question asking what of a molecule like is a constant regardless of other things.
Okay.
And I guess the pKa was the right option.
Okay.
Um, would the PI like change too, or would it be held constant rather?
Uh, so in the context of the question, what were like the, I guess, choices?
I think it was like pH, pKa. Uh, I think like the conjugate acid or something, or the base. I think those were the options.
Okay. Let's see. Um, so yeah, so pH is not going to really stay constant. Um, is that what you're saying? You're saying like one of these remains constant, like pH, pK, or PI?
Yeah,
Okay.
yeah.
So you're going to have, okay, so pH is not going to be constant. That's going to be dependent on that proton concentration only. And you could do a lot of things. You can drop a bunch of water in it and dilute it and get a weakened concentration value that way, with the same amount of moles of protons, but a lower concentration because you're diluting it. And that means you're going to get a higher pH, less acidic one. So you can certainly mess with that. Um, and also, our bodies kind of keep us regulated at a narrow, like our blood pH is like in a narrow range of like 7.3, 7.4 kind of thing. And that's because of the buffer system, like the bicarbonate buffer system, because a buffer is going to help something like pH remain more stable, right? So now, but yeah, for the most part, pH is super, super, it's not very constant at all. Now pKa though is an intrinsic property of that compound. So that's why we see here that this pH value relative to the pKa value determines if you're going to get something like protonated or not,
Hmm.
right? So that's going to so pKa is going to be mostly constant. Um, I guess theoretically it could change with temperature, but meaning you could help something dissociate more at high temperatures, which would therefore strengthen or make something more acidic. But
Mhm.
it's not gonna but also it does not change with um dilution. It's 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 the way that I think about it is if I had a beaker with a pH of something and I had my molecule, let's just say this is the molecule with a pKa or of something and I throw it in, the molecule will get either deprotonated, and that's if the pH is larger than the pKa, or the molecule can get protonated, and that's if the pH is less than the pKa. But you see how it's like the protonation or deprotonation or neutral nature of this molecule is determined by its relationship, its pKa relationship with the pH.
Okay.
So
And then,
pKa, yep.
well, then in that case, like if the pKa is an intrinsic value and the PI is based off of the pKa, would that also be constant too?
Yep, excellent deduction. Yep.
Okay.
Yeah.
Mm, okay.
Okay. Makes some more sense now.
Yeah.
Okay, so that was the
Um,
yeah. Were
did
you
we go through, I guess, maybe like the Arrhenius equation and what that is used for?
uh-huh. Okay, so that's going to be one of the only questions you'll see on or yeah, sorry. One of the only things that you'll see on the MCAT that has Euler's number, the little e.
Mm-hmm.
And what it essentially does is it relates a reaction rate with temperature. So
Okay.
yeah, so basically here, let me draw it like over here. So um it's like okay, K a constant is equal to Euler's number to the power of negative activation energy divided by RT. Oops. By RT. And you could like take like the natural log of this to get rid of that E, the Euler's number thing.
Mm-hmm.
And, what you can then see is so, okay, if I did I'll just do natural log of K is equal to natural log of A. Now, since I'm multiplying capital A by E, what would I do to the log?
Um, like, would it just be negative EA over RT?
Mm-hmm. I would subtract it, right?
Oh, yeah, because they're being divided.
Oh, I mean, so uh, between the A and the E,
Oh,
sorry, I get so like if I had, log of x times y, this would turn into what?
Um, you would add them.
Yeah, log of x plus log of y, right?
Mm-hmm.
So here I would add log of e to the power of this thing. So, but if you take the natural log of e, the e you get rid of that e, right?
Yeah.
So it'll just be like now
Oh, okay.
mhm.
So it'd just be minus BA over RT.
Good. Um yeah, okay. So this could also, all right, yeah, what can we do with this now?
Um, well, like, what is, are we trying to like get temperature by itself? Like, what are we trying to do with the equation?
Oh, I guess um finding the relationship between um the rate and activation energy, and temperature. I mean, predominantly, okay, so this lowercase k is the rate, and we're trying to see how rate can be determined by temperature. So if we, so from here, if we increase temperature, this entire value gets smaller or larger.
It would get smaller.
And now, since we're subtracting it, right, we're subtracting a smaller number.
Then K would get larger.
Exactly. So really the takeaway here is that uh K is, or yeah, rate is proportional to temperature.
Okay.
That's the end, like, bottom line of the Arrhenius equation. Um, but I've just seen lots of problems that required you to do something like to either get the E Euler's constant or do something with it. So I would just be aware of, like, being able to get rid of the E through natural log or adding the E and stuff. But yeah, for the most part, it's just the relationship between the rate and the temperature.
Okay.
Okay. So now, let's see.
Mm,
Uh now, okay. So our mechanical advantage, what can you tell me about that?
Um, it's like through the use of machines to like lessen the force, or I guess lessen the work that you need to perform to accomplish something.
Okay, so um if it takes wouldn't if it takes less work, wouldn't that violate the conservation of energy?
Or you're just dispersing the work. So it like feels like you're doing less work, but in reality, you're just kind of displacing it over a larger distance.
So if work is FD, using a simple machine will take advantage of distance. So first of all, work energy must be conserved whether you're using the machine or not. You're still ultimately doing the same amount of work.
Mm-hmm.
However, if you manipulate the distance, you can do the same work with a lower applied force if you use the machine.
Okay.
So that's the idea behind mechanical advantage, which would then be the ratio of your so input is if you're using the machine, output is if you're not. Oops. So whoops. Uh, output and then the output, the input. So like that problem we did before that was talking about like let's say this is 1 meter and you have a box of 1000 newtons and you want to lift it up to this, let's say this is like a stage or something. So if you were to lift it straight up, how much tell me about yeah, the work, the force, the distance.
Well, the distance would be 1 meter, and then the force would be um mg. So it would be 10,000.
So
So,
I wrote it as it's hard to see, but was trying to write hang on, fix it. 1000 newtons.
but times g would be 10,000.
What what would we multiply G by?
The mass.
Uh-huh. Is this
Oh,
uh,
um, that already is mg.
mhm. Yep. So yeah, you would so your work is your force times distance, which is 1000 newtons times 1 meter, right?
Mm-hmm.
Okay, now if this length of this ramp here is, let's say, 10 meters, and you use the ramp to bring this box, which weighs the same amount, up to the same height, what would the so the work will be the same.
It would be 100 newtons of force
Mm-hmm.
instead.
And so your mechanical advantage would be
Um, 900. Oh, wait, you divide the distance by the,
so
wait.
so for mechanical advantage, you're gonna want that number to be larger than one because think about it from the perspective of mechanical advantage. What
Mhm.
advantage do you get by using the machine? It's gonna have to be a number greater than one. One would be if you're not using the machine, and then less than one would be like, I don't know, if you're doing something like the opposite. But yeah, if it's greater than one, then that constitutes an advantage. So for the formula I wrote, I think I wrote, yeah, here, the force um of the oh wait, hold on. I did this backwards. My bad. Let me change that. So it's going to be your force output. And again, if you're using the machine, it's input. And if you're not, it's output. So force output over force input is also going to be equal to distance input over distance output. So how to tell if it's output over input or input over output, right?
Hmm.
Whichever one would give you a larger number, aka whichever one is larger would be in the numerator because we want our mechanical advantage value to be larger than one.
Okay.
So we can sit. So what can we put in for the force output here?
1,000 over 100.
Yep.
So the mechanical advantage would be 10.
Yep. And then same thing with distance input. If you use the machine is 10 meters over output. If you didn't use the machine, it's 1 meters, which again is 10.
Okay.
So think of the mechanical advantage as some value that's larger than one because it's an advantage that you're getting, which means and it functions also as a force multiplier,
Hmm.
meaning that if you use this machine, the force that you input um, gets multiplied by a factor of 10.
Okay.
Okay. And
Um,
yep.
there was a problem that I did where it was like on like a pulley system. Like it was like this is you, and then you have two pulleys here. Oh no.
I lost your where are you drawing this?
I'm drawing it like by the equation we just set up. Yeah, I don't know what
Where the
happened, but yeah, this.
Mhm.
Um, and then there was like another pulley, and it kind of went like this, like around this pulley.
Mhm.
Oh, it keeps like changing where I'm drawing.
Mm.
But there were two pulleys, like one on top of the other one.
Yep.
Um, and I got the answer right, but I was a little confused as to how.
Got it. Yeah. So even though we're using like the like okay, so like if we had um just let's say a box like hanging here compared to if we had like a pulley and we had something hanging like from that, it's kind of hard to see, but in making it go around the pull like part of the pulley circumference, we're increasing that length,
Mhm.
which is what we're typically going to see in mechanical advantage. But you could also just think of this as like the ratio of like the load and the effort you must put in to pull or to lift that load. And so that's going to be a way of calculating your mechanical advantage for like a pulley system. Um, and it also changes the direction of the force, which can also be useful. And so, yeah, this is going to be more so of a mechanical advantage of load over effort. And this is also proportional to the number of the pulleys or the number of supporting ropes.
So if you had two, like when you say the number of supporting ropes, like is one, like if you have a pulley, is that now two supporting ropes rather than one? Like if it's across the pulley.
Um, in the sense of like, wait. So yeah, okay. If we had something like here, oh, and then let's say this is attached to a load. Let's see. 1, 2, 3. Yeah, I think it'll just go like that. So each pulley should have two supporting ropes.
Okay.
Mhm. Yeah, there's also here, I'll write that down. Yeah, there's also like a good pulley problem that I went over with someone before, but I will it'll probably take me or actually, no, I found it. Okay. All right, here. Well, actually I'll have you do this for like homework or something, just because I want to get through some more of these. Um,
Mhm.
so for instance, all right, let's see. So now we did a little bit of the mechanical advantage and uh okay, expansion. So when things heat up, they expand, right?
Yeah.
And so okay, yeah. So basically, do you see where I am?
Yeah.
Okay. So like let's say we have the length of something, and then this alpha is the coefficient of linear expansion times the change in temperature times the original length. So basically, this is showing you that you're going to have length expansion, or
Hmm.
sorry, linear expansion as a consequence of heat causing things to expand. You could also have like area expansion, which you could imagine. So length is in one dimension, area is in two dimensions. So this will just be like 2 times the alpha term, delta t, a naught, original area. And then lastly, volumetric. What do you think this would be?
Three.
Mhm. And
So
then,
you can square or cube anything.
no.
It's okay.
Because we're really just applying this once for one dimension, again for the other dimension, and then one more time for the third dimension,
Okay.
right? So, yeah, so that's why we're not doing like squares and stuff. But yep, that's linear and volumetric expansion. And, I've seen a question like that in the section bank, volume 2, which
Did
you,
they did they actually ask you to calculate something, or is it more so just knowing the relationships between variables?
Um, the one that is on that like asked you to calculate. Um, so and
Okay.
also they didn't give you like this, so it's a little weird like that. But okay, that should be that. Kinetic energy of a photoelectron is pretty important, as are have we gone over like photon absorption, excitation, and then like fluorescence, and then like work function photoelectric effects stuff?
Uh, Briefly, I think
Hmm.
I'd like to cover a question, but um, not super in depth, I don't think.
Got it. So let's say that we had N1, N2, N3, and okay, let's say that. So N1, N2, N3, let's say that the energy difference between the first two shells is 1 electron volt, and between these is 0.5 electron volts. Now, if I shoot a photon at this atom with 0.99 electron volts, what would happen?
Um, it would cause the like an electron to move into an excited state, like move up
So,
in
what energy do we need to move up a shell?
0.5
Oh,
or
sorry. We're starting at, so we're talking about electrons in the ground state, starting
uh,
at N1.
so you would need 1 electron volt,
How many do we have?
0.99.
So what can happen?
Nothing.
Hmm. Yeah, like it it doesn't come up to like 99% of the way, right?
Yeah.
Nothing happens, right? All right. What if we shot two? Now what?
Then it would jump to N3.
Okay. So if atoms behave this way, where each photon would cause an electron to jump, we have light, like right now, light is like you're having like trillions of photons hitting you from like your computer screen, from the light, above you, everywhere. You have like trillions of photons just boom, 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 boom. But it's not like we're like dying or anything, right? So actually, it doesn't matter if we have two or 2,000. They still do not meet the necessary requirement for the electron shell transition.
Why is that? Like, why wouldn't they have an additive effect?
So that's why it's called quantum mechanics, because the quanta or quantum refers to a discrete energy packet that is not that is only like stepwise. Like there's no in between. There's no like, it's yes, it's all or nothing because that's good. I mean, like it comes down to like the fact that the difference between one shell and the next shell is the energy required to go from one shell to the other shell. And it's not like there's like this safety net underneath the N2 shell for the electrons to hang out at. Like they can only go from like one shell to another shell. They can't really, there's no area for them to hang out in between.
Okay.
Mhm. So something that they like to ask, and this is like everything that I'm about to show you is going to be very high yield. You'll see it all the time. But something they like to ask is, what if we raise the intensity? Would that make this photon or these photons absorbed?
Uh, no.
Because intensity corresponds to the number of photons, and we just talked about how if you have whether you have one or two of these doesn't matter. So the number of photons don't matter, which means that the intensity doesn't matter, right? So good. So now let's say we shoot a photon with energy of 1 electron volt, and actually have a good, I guess, comparison analogy for your question about why they're not additive. Um, let's say you have HCl, or let's say that you have like carboxylic acid, which is a weak acid, plus sodium hydroxide, a strong base. Um, you could have, and okay, let's say that you're trying to neutralize the sodium hydroxide with this weak acid. Um, that's going to be very tough. Like you're going to need, like you're probably going to throw in like trillions of molecules of COOH to completely neutralize the sodium hydroxide. Whereas instead, you could just use HCl. So if you had 10,000 trillion, whatever, maybe not trillion, but some high number of the weak acid, it will barely dent, the high pH of sodium hydroxide. Whereas if you just had one molecule of a strong acid like HCl, it will neutralize the NaOH. So, you know, that's the idea. So, okay, if we shoot a photon with 1 electron volt, what will happen now?
It will be excited and go into the N2
What will
orbit.
be excited?
The electron.
Okay, so think about it like this, right? The photon has 1 electron volt of energy. The atom can absorb that photon and add to its own energy 1 electron volt of energy. And it expresses that by exciting an electron from N1 to N2. Boom, up here, right?
Mm-hmm.
All right, now things that are of a higher energy level like almost by definition are less stable. So it's going to want to relax back down to the ground state. But now, since it's going back to the original energy level, it doesn't need that extra energy from the photon anymore, so it'll emit that energy as a photon. So the energy of a photon absorbed will be equal to the energy of a photon emitted, right?
Mm-hmm. And it'll do that immediately after it absorbs.
Maybe not immediately, but eventually it'll do it just because it's going to be less stable if it has a higher energy.
Okay.
So, okay, this is scenario one in which you just have your conservation of energy. Now, if you have a molecule with a lot of conjugation and like lots of um, dyes and pigments will have will look kind of like this. This is like melanin, like the skin pigment.
Mm-hmm.
And this is also going to be related to UV vis, where it recognizes or detects triple bonds and like conjugation, like triple bonds and double bonds. Because, well, I'll get to that. Why? So now I'm going to use blue. So let's say we shoot a photon with an energy of 1.5 electron volts. What'll happen now?
It'll move to M3
Good. So now if the molecule is highly conjugated like this, it means what? Like what do I mean when I say conjugated?
um like it's more stable.
Yep.
It has like alternating double and single bonds.
Tell me how that would make it more stable.
Um, Something about like the p orbitals overlapping
So like for instance, let's say we have benzene. Why is benzene like so stable?
because it has resonance.
Yep. So conjugation, aka alternating double bond, single bond, double bond, has resonance, and resonance, other words for resonance are, well, of course, conjugation, conjugated pi bonds, electron delocalization, because you're spreading that electron orbital like across a larger area. So it's always going to cause stabilization. So what can happen for these types of molecules with a lot of conjugation is they can absorb this 1.5 electron volt photon, but through its own, and like it'll cause it to shoot up to here or excite up to here. But due to the molecule's own resonance stabilization, it can dissipate some of that excess energy off to the environment, thus reducing its energy level, let's say down to the N2 shell. So zero point 0.5 electron volts have been dissipated, and like they could use words like through vibrations and stuff. Like that's one of the things that they can say, but it's
So,
yep.
like when it's dissipated, it's not like dispersing the energy throughout the molecule. It's like dissipating it into the environment.
Yes.
Okay.
Hmm. Yep. And so it can enable the electron to relax down a shell, but unlike here, it can do that through that resonance vibrations rather than emitting a photon. Okay.
So the amount of energy that is in the molecule would still be the same.
Um, when you say that,
Like it goes, hmm, I don't know, like it goes down into a lower energy state, like by vibrating. Like that's how it gives off the energy.
yeah. So it can give off some of that energy through that to, let's say, bring it down to N2. But after it's done that, after it's dissipated that energy, right, it can then go from N2 to N1 the normal way. which involves emitting a photon.
Mm-hmm.
But now, what would the energy of the photon be?
Um, one.
Mm-hmm. So, if you have fluorescence, the energy of the photon absorbed would be greater than the energy of the photon emitted, which would mean the wavelength of the photon absorbed is less than the wavelength of the photon emitted, right?
But if it's going into what, so you're saying like first the molecule vibrates and then it goes down? Like what happened to the 0.5 when it was originally in N3?
So so at N1, it's like, okay, like let's say that you're at N1 and it's like, okay, MCAT's coming up. You're gonna feel perhaps like, I don't know, like let's say like anxious or something. And because you're just given this 1.5 electron volt, photon and you're asked to like, deal with it. And like let's say that, it makes you more excited, which means you're more, could possibly mean, let's say you're anxious. And like let's say then you like do some like Zen meditation to help relax you from N3 to N2.
Mm-hmm.
Then you can relax from N2 to N1 by doing the regular thing, which is emitting a photon. But since you did that in between Zen meditation, you get to lower that overall energy level through other means. When I say other means, I mean means that are not the emission of a photon.
Okay.
So now UV vis works in that same way because UV light, you shoot at it, and if it has conjugation, it will absorb that UV light, which is high energy, but through its own resonance stabilization, it'll lower that energy a bit so that when it emits light, it's of a lower energy. So if you have UV light absorbed and visible light emitted, that means the energy of the light emitted is smaller than the energy of the light absorbed. So they'll say things in passages like this was excited at 420 nanometers and it emits at 570 nanometers, something like that. Okay, so that's fluorescence, super high yield, and then the last scenario of making green is what if we shot a photon, let's say, with 2 electron volts? Now what can happen?
Um, I mean, if it doesn't have an N4, uh, would the electron be given out? Like the electron leaves?
This is called the photoelectric effect. And what this means is, so basically, so this was like Einstein's first Nobel Prize. Like, let's say you take a sheet of aluminum foil or something, you attach wires to it, which are attached to a light bulb, and you take a laser and you shoot the laser at this metal sheet. Now, depending on something called the work function, have you heard of that before?
Yes.
So we could think of that as like the ionization energy of that metal. So if we shoot a laser with enough energy, so the formula here is going to be kinetic energy of an electron is equal to the energy of the photon minus the work function. And so if you have the a photon's energy, let's say the photon's energy is equal to the work function, that electron will be excited to, I'll use orange here. It'll get excited to the n is equal to 3 shell, and it'll even be unbound from that shell, like from the atom rather, but
Mhm.
it still doesn't have any energy to move. But if the energy of the photon is larger than the work function, that excess energy gets converted into the electron's kinetic energy. Okay. So if we are shooting this sheet of metal with a laser whose photons are larger than the metal's work function, the electrons will not just get excited, they will be eject and not just get okay, so not just get excited and not just get unbound, but get ejected and shot out with a velocity. So that means that the electrons can then leave the metal, travel through the wire, light up the light bulb and close the circuit, right?
Mhm.
So that's called the photoelectric effect. And that's what you wrote, or yeah, what you wrote over here. Kinetic energy of a photoelectron.
So the equation for that, like I'd never seen it before. But
This.
yeah,
Mhm.
like what does that mean?
Oh, so that's just so it's what I same one I drew here. You see it?
And like the like you're subtracting what was the other variable for again?
Oh, this one.
Yeah.
So that's the called the work function,
Oh.
and you can think of it as like the ionization energy. So that's the energy of the outermost shell.
Hmm.
So if your photon energy is equal to that work function energy, kinetic energy of the electron is zero. So it's not like it's being ejected, but it does mean that it's no longer bound to the atom. But if
Okay.
your photon's energy is larger than that of the work function, then you will have a kinetic energy of the electron term, which means that the electron is not just excited, is not just unbound, but it's ejected and moves with some velocity.
Okay.
Mhm. So these are the three things for for photon absorption and stuff.
Could I take a screenshot of this?
Yeah, so at the end, I'm just gonna have you export the entire PDF.
Oh,
Yep.
okay.
So, okay, so that was that. Now, let's see. Um, I've never seen like the electrode deposition thing or Van der Waals thing. I mean, other than, the concept. Heat capacity, I mean, what can you tell me? Like, what's your conceptual conceptualization of heat capacity?
Um, is it the amount of energy it takes to like increase the temperature of a like mole of a substance?
Yeah, so, if it's specific, it's going to be like the energy it takes to raise a gram of something by 1 degree, Celsius. But yeah,
Mhm.
like conceptually speaking, it's how much heat can something hold before it goes up in temperature. And so like water is a good example of one because if you think about it, like for instance, like what's a desert?
A desert,
Yeah.
um, like the absence of water
Hmm. So, uh, during the day, what's the temperature like typically?
in the desert, very hot.
And at night?
It cools off a little,
Uh-huh. Is it still relatively hot or is it like pretty cold?
relatively hot.
So it'll be pretty cold,
Oh,
right? Now, why is that, right? So water has a high heat capacity. So during the day, the water can hit the sun, sorry, the sunlight can hit water vapor and stuff just in the air, like if we're talking about not a desert. And that can, like, since it absorbs so much heat, it can make it feel not that hot during the day if you're in a not a desert, um, because it absorbs that heat. But it also means that at night, when there's no more, sunlight causing the heat, the water can release some of its heat. But all in all, water is going to be, its temperature isn't going to be fluctuating too much because it has that high heat energy or heat capacity rather. Um, so yeah, so a desert is not going to have that water. So at during the day, it's going to get really hot. But at night, there's nothing holding on to that water that to kind of give it off. So at night, it's going to get super, super cold. So that's why uh that's why it can get really cold in like Ohio and stuff. Um and like Siberia, right? Even compared to regions of the Earth that are even higher latitudes because they're like essentially landlocked and away from bodies of water. And bodies of water, due to the heat capacity of water, can act as a buffer, like a heat buffer or a temperature buffer.
hmm.
So that's heat capacity. Specific gravity is the density of some object or fluid or anything divided by the density of water. Um, and the density of water is like know the different values like 1 gram per milliliter, a kilogram per liter, all those different values. But specific gravity questions can get pretty tough. You did one recently that I sent you, which I can look at. Pascal's law is so real fluids versus ideal fluids. What can you tell me about them?
An ideal fluid would follow like PV equals nRT.
Oh, you're thinking of ideal gas,
Oh, yes. Sorry.
but for ideal gas, you should also know like what separates an ideal gas from a real gas. Um, but okay, yeah. Tell me what you're saying about
Um,
real fluid versus ideal fluid.
an ideal fluid, I
Hmm.
think, is like it flows the same in every like part of the fluid, if that makes sense. Like the velocity of the fluid is equal, I guess,
So
or uniform, maybe.
so a real fluid will have viscosity.
Oh.
Okay. And viscosity you could think of as like, let's say for a fluid, you can think of layers of the fluid as having friction, keeping them kind of closer, like tighter together so that there is less of like flow and actually less like possibility of turbulent flow. Um, but you're gonna see, so an ideal fluid is gonna give you like a flat wall, whereas in a real fluid, it's going to be more like this because you're considering the fact that at the edges, like the water or whatever fluid at the edges of the pipe here have friction with those pipes and they travel slower compared to the ones in the middle. So this will produce a bowed shape like that. So, but yeah, what distinguishes a real fluid from a ideal fluid is viscosity. Viscosity is in real fluids and not in ideal fluids. So what that could also mean is that um, so for the ideal fluid, you can use your continuity equation of, A1 B1 is equal to A2 V2.
Mm-hmm.
You could also use Bernoulli's equation, which is simply conservation of energy applied volumetrically to fluid dynamics. That could be like constant is equal to like P times 1/2, whoops, rho V squared plus rho G H. Um, but your real fluid that's the one that's going to involve Basile's law.
Mm-hmm.
And I'll get a picture of that. So
Do they typically provide the equation or you just have to know it?
I think
I've seen whenever I've had something like this, they typically provided.
uh-huh. Yeah, they'll likely provide it for you, but I would also just kind of remember that it's one of the few Basile's law is one of the few equations that has such a high exponent value in it, like r to the fourth power.
I like when I was trying to figure out how to memorize the equation, sometimes I would see the numerator and the denominator switched, and it just really confused me, like which one is correct.
Hmm, interesting. Yeah, you could show me that when you get the chance, but yeah, you should essentially see your like so yeah, also like this goes for all equations. Like I want you to be able to see like or think like, okay, flow rate, like your volumetric flow, like if you increase the radius of a pipe, your it should make it easier for things to flow through them, right? Kind of just how we talked about maybe last time about how in a wire, if you have a larger area, there's more paths for like the electrons to flow through. So you should be able to tell like, that this flow, volumetric flow should be proportional to the area, which is kind of like what this is saying. But the longer it is, the more friction will happen to it. Just like in a resistor, the longer the resistor, the more resistance. So you should
Yeah.
see the length as being in the denominator. And also, viscosity is a resistance to flow. So you should see that in the denominator as well.
Okay.
And then the last thing would be turbulent flow. And here's a picture. So we have laminar flow, which is the bowed shape, and turbulent flow, which is like whirlpools.
Mhm.
Let me find a better. Here's like another one like this. So now the turbulent flow happens. There's something called Reynolds number, but it essentially, so turbulence is going to be inversely proportional to this, which is viscosity. Because if you kind of imagine it, if there's more friction between like the layers of the fluid, it's going to be more difficult for the fluid to start to go like twist around in whirlpools and stuff,
Mhm.
right? So that's turbulent flow. And yeah, so I guess I guess center of mass is just going to be like I guess that'll be the last thing I'll go over really quickly. So like center of mass, like okay, let's see. Um in general, let's say I have this long stick or something and it's made out of some uniform material. It's gonna have uniform density throughout the entire thing. So in a free body diagram, I can just draw the vector, gravitational vector just going down in the middle. But
Mhm.
if I had something like, let's say it's a sword, um, the where this is the metal, right? This is the handle. The metal part's going to be heavier. So the center of mass here is going to be not in the center, but further to like the tip, right?
Yeah.
So what they actually do is they make something on this end called the pommel, which they also use to like attack people. That's where like pummeling someone comes from, like hitting them or whatever. But they would add the pommel to also act as a counterweight to increase the density at this end to bring this closer to that like handle to make it more maneuverable.
Mhm.
So so yeah, center of mass for a uniform object is literally going to be in the center. But for a non-uniform object, meaning an object without uniform density, it won't be in the center. And if it's not in the center, it's going to cause a torque. It's going to cause a rotation.
Okay.
Okay. So that's center of mass. So next time I'm going to have, or in between now and next time, I wrote down mechanical advantage problems other than just inclined plane, like pulley.
Mhm.
And this let's see. Oh, and then yeah, I guess so what other types like of questions would you
Okay.
want me to
Like the more fluid questions with density.
Mhm.
Um, maybe some questions on like I know you suggested the thermodynamic uh Jack Weston ones, which I'm planning on doing like tomorrow or the day after. Um,
Mhm.
so I'll do those and then maybe um,
Okay. Yeah. So I'll send you some problems regarding this stuff. And oh, and then yeah, and then next time maybe like in the first like 10 minutes or so, I'll just have you kind of explain to me some of these concepts. Oh, you like froze for a sec.
yeah, I
Did
think
you?
you just posed it.
Yeah, I saw you go from like here to here,
Oh
like
yeah.
teleported. So sorry, what was that? So, oh yeah, like in the first like 10 minutes of our next session, I'll have you explain some of this stuff. So,
Okay.
okay, now you could go up on the top left of the whiteboard, and there's like a three horizontal lines
Hmm.
If you that says more, if you hit that, it'll open up a drop down,
Yeah.
and there's an export option, and you can export this into PDF form.
Mm, that's locked.
What's up?
There's no, I think only you can do that because you're the like the host.
Oh,
Because I don't have any like I don't have any way to save it.
okay. Here, I'll export it. And in the chat, well, you froze for. Oh no, you're back. Okay. I did it for you. I put it in the chat, so you can download it from there. Tell me if you see it.
Um, yes. Okay. I got it.
Okay, awesome. So let's see. Let me see. I'm seeing you next. Did you schedule something for next time or? Oh,
Yeah, but I think it was
the first, I think. Saturday.
yeah, Saturday.
Got it. And between now and then, I think you'll be doing another full length, was it?
Yeah, I'll be taking the next one on Friday. Like next Friday.
Next Friday, you mean on the 28th?
28th.
Got it.
Yeah.
Well, we're not taking one this weekend because you took them like during the week or something?
Um, Friday through Sunday I have work.
Okay,
I'm not able to.
got it. Okay. So you got the whiteboard thing?
Yeah.
Okay. And yeah, you can send the payment.